Hello Queen students, my name is Levi and I'm the Wizeprep for Phys 117. I graduated from Queen's a few years ago and I was a physics major, which means I took basically every course that's offered in Sterling Hall except for the one you're taking now, because none of you want to major in physics. And that's okay, and I understand that, and I'm here to help you cross the finish line as gracefully as possible. After my undergrad, I actually did a master's degree in medical physics, working with CT and MRI imaging, as well as radiation therapy treatments of cancer patients. All really interesting stuff, and it all relies fundamentally on the stuff you're doing now this semester. The M in MRI stands for magnet, so you can be sure that electricity and magnetism do matter in the real world. So please feel free to check out the rest of this free preview. I've worked with lots of students before. I TA'd a bunch of students in similar positions as yours, not necessarily wanting to take physics, but working hard to do well in it anyway. I really enjoyed working with students like you, especially, who are just doing physics for the first time. I know it can be intimidating. Feel free to ask questions at any point. I will get back to them within 24 hours. Another really important concept in magnetism is that a wire will exert a force on another wire. And in this video, I'm going to try to convince you why that has to happen. So here I have a picture of two wires on the left. I'm actually going to build this up from scratch. Let's use this white space down here. Let's say I have two wires and their currents are in the same direction. So I'm going to call this I1 and this is I2. You know that a wire will produce a magnetic field. So if we look over here, we wrap our fingers around I1, what we're going to get is a field that goes like this. So what I should really write here, it's coming out of the page on this side and into the page on that side. So you should put your thumb right now in line with my I1 here and see that the field has to go into the page over here. So what that means is that if we have a second wire over here, there is a field pointing into the page at I2. So let's just look at this then. So here we have a current I. We have a field into the page. And now I want to ask you, what's the force on that wire due to the magnetic field? Well, F is equal to IL cross B. IL cross B. So L cross B, or you put your fingers in the direction of the current, and it's going into the page. So what you get is the force, you get a force going to the left, and you get that using the right-hand rule. So what we've just determined here is that wire 1 will exert a force on wire 2 because of the field pattern that it makes. So that is the force on that wire. And what I want you to do, pause the video if you want, do the exact same analysis that I just did, but the other way around. Figure out which way the field, because of wire 2, what direction it is, and tell me the direction that the force on wire 1 has to be due to the second wire. And what you're going to find, spoiler alert, is the force points to the right. What if I2 was pointing the other way? Well, in that case, let's just get my blue pen again for the wires. I1, I2. The magnetic field from I1 is the same. So the field, I'll do it in red again, over there is into the page. Right-hand rule, put your thumb in the direction of the current, field goes into the page. But now my current is going down. Current is going down. So if the current is going down, again, we're going to use the cross product formula. So put your fingers in the direction of the current, which is downwards, and then point them into the field. You'll find that the force from your fingers is going to the right. And if you do this again over here, you're going to find the force is going to the left. So just by using the two right-hand rules, the right-hand rule that you use to get the magnetic field direction from a wire, and the right-hand rule that you use to determine the direction of a force due to a charge in a field, you're going to find that if you have two wires going with current in the same direction, then they attract. If the currents go in the opposite direction, then they repel. And what is the value of those forces? Well, the value on those forces, let's just think about it. So it's IL cross B. B is going to be mu naught I over 2 pi r. We're multiplying that by IL. So it's just IL cross B, and the sine theta part goes away again because everything in this case is perpendicular, in this example anyway. So what we'll often do in questions like this is instead of talking about the force, we'll talk about the force per unit length exerted on the wires. So what you find then is F divided by L equals mu naught I1, I2 over 2 pi r. So that's where this formula comes from. That's the magnitude of the force per unit length that a wire exerts on the other wire. R is the distance between the two wires. Here's an example that I like a lot. So we have a 25 centimeter long straight wire on top of another wire. So we're assuming it's directly above the other wire, carrying a current of 2 amperes as shown below. The top wire is 5 millimeters above the bottom wire. What is the electric current of the top wire, and in what direction is it if the top wire weighs 0.25 grams? I should say weighs. So the idea here is that you have this object where the net force is 0 because it's lying motionless, it's not accelerating. So we know that there has to be a force downward from gravity, mg, but there's also a force upward, and I'm just going to write FB to represent the magnetic force on that wire. So the question is asking you how the magnetic force can cancel the gravitational force. It's kind of a Newton's second law problem, not really a kinematics problem, but you still have to understand the concept of forces canceling out. So it's mg equals that. So how do we determine, first of all, how do we determine the direction of the current? Well, we know that the magnetic force has to be pointing upwards, and we know that wires only repel each other if they go in the opposite direction. So we know that the current has to be going to the left. If the current goes to the left, then we have them going in the opposite direction, and then they repel each other, and that's how we get this repulsive force to cancel out gravity. So now we've finished the direction. Now let's talk about the magnitude. We know that the force per unit length is mu naught I1, I2 over 2 pi r. And we know most of these values, by the way. And we're saying that the wire on top has it's 25 centimeters long. So let's just write it this way. We're going to write the force is equal to this times L. So that's the value of the force, and we know that that force has to be equal to mg. And what we're asking for is the magnitude of the current. So it doesn't actually matter which one we call I1 and I2 here. The math is the same. Let's just say this is I1 and that's I2. So I'm trying to find I2. So let's just put all the variables over. So multiply by 2 pi r divided by mu naught IL times mg. That's how we get the value of the current. Then we just plug everything into this. Although let's do this carefully because some of the units here are kind of funny. So it's 2 pi. R is 0.005 meters because it's 5 millimeters. G is easy. Let's just do that. Meters per second squared. The mass was given in grams. It's 0.25 grams, but we want it to be in kilograms. So make sure you times that by 1 over 1,000 to get 0.00025 kilograms. All of that is divided by 4 pi times 10 to the 7 Tesla meters per ampere times the first current, which is 2 amperes, times 25 centimeters, which is 0.25 meters. So just make sure that you make these substitutions properly. The units here should all cancel out, and what you're going to get in the end is amperes, and the value is 120. It's about 123 amperes that you're going to get. 1, 2, 3.